Top 25 Machine Learning Engineer Interview Questions and Answers. If you're preparing for a machine learning engineer interview, this video will walk you through the top 25 questions and answers that interviewers love to ask. Whether you're aiming for a role at a tech giant or a startup, understanding these concepts will help you confidently showcase your knowledge. We'll cover real-world ML challenges, model optimization, and practical coding insights. 1. What is machine learning? Machine learning is a subset of artificial intelligence that enables computers to learn from data and improve their performance without explicit programming. It uses algorithms to detect patterns, make predictions, or automate decisions. There are three main types: supervised, unsupervised, and reinforcement learning. For example, in spam filtering, the model learns from labeled examples to identify unwanted emails. The more data it processes, the better it becomes at recognizing new patterns. 2. What are the different types of machine learning algorithms? Machine learning algorithms fall into three main categories: supervised, unsupervised, and reinforcement learning. Supervised learning uses labeled data for prediction, like regression or classification. Unsupervised learning finds hidden patterns in unlabeled data, such as clustering or dimensionality reduction. Reinforcement learning involves an agent learning through trial and error to maximize rewards. Each type has unique use cases, from predicting stock prices to enabling autonomous driving. 3. Explain supervised learning with an example. In supervised learning, the model learns from labeled input-output pairs to predict outcomes for new data. For instance, if we train a model with features like house size, location, and price, it can predict future home prices. Algorithms like linear regression, decision trees, and support vector machines are commonly used. The key is minimizing the difference between predicted and actual values using loss functions and optimization techniques. 4. What is overfitting, and how can you prevent it? Overfitting occurs when a model learns noise or random fluctuations in training data, reducing its ability to generalize to unseen data. It performs well on training sets but poorly on test sets. To prevent overfitting, you can use techniques like cross-validation, dropout, regularization, L1 per liter 2, or simplifying the model. Gathering more diverse data also helps, ensuring your model learns meaningful patterns rather than memorizing training examples. 5. What is underfitting? Underfitting happens when a model is too simple to capture the underlying structure of the data. It performs poorly on both training and testing sets. This often occurs when using insufficient features or overly simple algorithms like linear regression on nonlinear data. To fix underfitting, increase model complexity, add more relevant features, or train the model longer. The goal is to strike the right balance between bias and variance. 6. What is the difference between classification and regression? Classification predicts discrete categories, like spam or not spam, while regression predicts continuous numerical values, like house prices. Classification models use algorithms like logistic regression, decision trees, and random forests. Regression models rely on methods like linear regression or support vector regression. Both aim to minimize errors but use different evaluation metrics: accuracy or F1 score for classification, and RMSE or MAE for regression. 7. What is bias-variance trade-off? The bias-variance trade-off describes the balance between a model's simplicity and complexity. High bias means the model is too simple and underfits, while high variance means it's too complex and overfits. The goal is to find a model that captures underlying patterns without memorizing noise. Techniques like cross-validation, regularization, and using ensemble methods, like random forests, help manage this balance for better generalization. 8. What is cross-validation, and why is it important? Cross-validation is a resampling technique used to assess how well a model generalizes to unseen data. The most common method is k-fold cross-validation, where data is divided into k subsets. The model trains on k1 and tests on the remaining fold. This process repeats k times, and the results are averaged. Cross-validation helps detect overfitting, improves model performance estimation, and ensures the chosen model is robust. 9. What are confusion matrix and its components? A confusion matrix is a performance evaluation table for classification problems. It shows true positives, TP, true negatives, TN, false positives, FP, and false negatives, FN. From it, you can derive metrics like accuracy, precision, recall, and F1 score. For instance, in a disease prediction model, TP represents correctly identified patients, while FP shows healthy individuals wrongly labeled as sick. 10. What is precision and recall? Precision measures how many of the predicted positives are correct, while recall measures how many actual positives were correctly identified. In medical diagnosis, precision ensures fewer false alarms, while recall ensures no real cases are missed. A balanced F1 score, the harmonic mean of precision and recall, helps evaluate performance when dealing with imbalanced datasets. Both metrics together give a clearer picture than accuracy alone. 11. What is feature selection, and why is it important? Feature selection identifies the most relevant variables that influence model outcomes. Removing irrelevant or redundant features improves accuracy, reduces training time, and prevents overfitting. Techniques include filter methods, like correlation tests, wrapper methods, like recursive feature elimination, and embedded methods, like lasso regression. The goal is to simplify the model without sacrificing predictive power, ensuring better interpretability and performance. 12. What is normalization and standardization? Both techniques scale numerical data but differ in approach. Normalization rescales values to a 0, 1 range, commonly used when features have different units. Standardization, on the other hand, centers data around the mean with a standard deviation of 1. It's ideal for algorithms assuming normally distributed data, like logistic regression or S versus M scaling ensures faster convergence and balanced feature importance during training. 13. What are hyperparameters in machine learning? Hyperparameters are external configurations that guide how models learn, unlike internal parameters learned during training. Examples include learning rate, batch size, tree depth, and number of epochs. They control the learning process and model complexity. Techniques like grid search, random search, or Bayesian optimization help find optimal values. Proper tuning ensures better accuracy and prevents underfitting or overfitting. 14. What is gradient descent? Gradient descent is an optimization algorithm used to minimize loss functions in training. It iteratively updates parameters in the direction of the steepest descent based on gradients. The learning rate controls how big each step is. Too large can overshoot, too small slows convergence. Variants like stochastic gradient descent, SGD, and ADAM add efficiency and adaptability, making it the backbone of deep learning model training. 15. What is regularization? Regularization is a technique to prevent overfitting by penalizing large coefficients. It adds a penalty term to the loss function. L1 regularization, lasso, encourages sparsity by forcing some weights to 0, while L2, ridge, smooths coefficients without eliminating them. Combining both creates elastic net. Regularization helps models generalize better by discouraging overdependence on any specific feature. 16. Explain the difference between bagging and boosting. Bagging, bootstrap aggregating, trains multiple models independently on random data subsets, then averages results. Random forest is a prime example. Boosting, like AdaBoost or XGBoost, trains models sequentially, each correcting previous errors. Bagging reduces variance. Boosting reduces bias. Together, they enhance model robustness and accuracy. The key difference lies in their training approach, parallel versus sequential learning. 17. What is a confusion matrix used for in ML? A confusion matrix summarizes prediction results for classification models, showing true and false outcomes. It provides insight into where a model misclassifies data, allowing you to adjust thresholds or retrain using balanced datasets. Beyond accuracy, it helps calculate precision, recall, specificity, and F1 score, giving a comprehensive performance view. It's especially useful when dealing with imbalanced data. 18. What is a decision tree algorithm? A decision tree splits data into branches based on features that provide the most information gain. It's intuitive and easy to interpret. Each internal node represents a feature test, and each leaf node gives an outcome. Although decision trees can overfit, techniques like pruning and ensemble methods, random forest, XGBoost, enhance performance. They're widely used for both regression and classification tasks. 19. What is ensemble learning? Ensemble learning combines multiple weak models to form a stronger predictor. The idea is that diverse models capture different data aspects, improving overall accuracy. Methods include bagging, boosting, and stacking. Random forest, AdaBoost, and XGBoost are common examples. Ensembles reduce variance, bias, and overfitting, making them popular in competitions like Kaggle for producing high-performing predictive models. 20. What is a confusion matrix imbalance problem, and how do you handle it? When one class significantly outweighs others, the model may become biased toward the majority class. This leads to misleading accuracy. To handle imbalance, use techniques like resampling, oversampling the minority or undersampling the majority, SMOT, or class weight adjustments in algorithms. Additionally, focus on metrics like F1 score, ROCAUC, or precision recall curves instead of raw accuracy for fair evaluation. 21. Explain principal component analysis, PCA. PCA is a dimensionality reduction technique that transforms correlated features into a smaller set of uncorrelated variables called principal components. It identifies directions, components, that capture the most variance in the data. PCA improves computational efficiency, reduces noise, and helps visualize high-dimensional data. However, interpretability can be lost since components are combinations of original features. 22. What is the difference between deep learning and traditional ML? Traditional machine learning relies on handcrafted features and shallow models like decision trees or SVMs. Deep learning, however, uses neural networks to automatically learn hierarchical features from data. While ML works well with structured data, DL excels in images, speech, and text. Deep learning requires more data and computing power but offers superior performance on complex tasks like natural language processing or vision. 23. What is reinforcement learning? Reinforcement learning trains an agent to make decisions by interacting with an environment and receiving rewards or penalties. The goal is to maximize cumulative reward. It's used in robotics, gaming, and self-driving cars. Algorithms like Q-learning and deep Q networks. DQN balance exploration and exploitation to find optimal strategies over time through continuous feedback. 24. What evaluation metrics are used for regression models? Common metrics include mean absolute error, MAE, mean squared error, MSE, and root mean squared error, RME, for measuring prediction accuracy. R squared shows how well the model explains variance in the target variable. These metrics provide insights into model fit. Lower errors indicate better predictions. Choosing the right one depends on whether large errors are more costly than small ones. 25. What are some real-world challenges in machine learning? Common challenges include insufficient or biased data, overfitting, model interpretability, and scalability. Data quality heavily impacts model performance, garbage in, garbage out. Deploying models also involves monitoring for drift and ensuring fairness. Addressing these issues requires careful preprocessing, ethical considerations, and continuous model updates. The best ML engineers not only build models but ensure they stay reliable in production. Preparing for a machine learning engineer interview takes more than just memorizing answers. It's about understanding concepts deeply and applying them in real-world scenarios. Review these questions, practice hands-on projects, and you'll stand out in any technical discussion. If you found this helpful, don't forget to like, share, and subscribe for more interview preparation videos. Your dream ML job might be closer than you think. Keep learning and stay curious.